Dr. Misra, I would like to ask for permission to initiate the second webinar session of this lecture series. Before I begin, I would request all the viewers who are not participating to please turn off their cameras and microphones throughout the lecture. Good morning and good afternoon, ladies and gentlemen, hailing from different time zones across the globe, all united by a common thread here today, that is geology. I am Rheological, member of Geological.
We don't have any meaning of Sunday in this changed time, but still it's a Sunday. So thank you very much, and thank you the students of Geological Institute of Presidency University. You have done a commendable work in organizing this lecture, and I also thank the students and also the faculty members to include me in the speakers list of this star-studded very well accomplished researchers of our field. So I feel a little embarrassed to be named with them, and today I decided to present something of some of my research which are very close to my heart, and at the same time something I would like to continue in IIT Kanpur. So yes, this is my email address. So this is particularly for the students. If you have any questions after this talk that you cannot ask through this online platform, feel free to write me. I'll try my best to answer your question. So the first slide is something about me, but this has already been said. Yes, I studied in Jadavpur University. Then I was in ETH Zurich in Switzerland. I also worked in GNS Science and also in Victoria University in Wellington, New Zealand. I'll present a little bit, advertise my activities in IIT Kanpur, then I'll go to the actual topic. So in IIT Kanpur, I mostly work in two directions together with my students and collaborators. So one segment is kind of fundamental research where I try to work on topics like earthquake mechanics, high-speed fracturing, some field-related investigations, particularly in, if you like, sequences in northeastern Himalaya, and of course, high-pressure, high-temperature rock deformation experiments. I also run sort of a parallel research in applied directions, and there I work on CO2 sequestration, coal bed methane recovery, and also I recently started on fracking and induced seismicity. So this is some of the students that work in the laboratory. So the most important person here is Rahul, who actually takes care of the lab and the entire daily routine. These are the students, Manav and Sakib. They will be submitting their thesis soon. And also among the MTech students, Gaurav and Himanshu, they recently defended their MTech thesis. You may see that, or you may think that this is a pretty male-dominated laboratory, and the data also say so. But there is no biasness. So girl students can always apply and work in the laboratory if you get a chance. So please do apply and join here. I also don't like a male-dominated lab. These are some of the instruments that we have built in the laboratory, some workshops, very basic deformation setup with a triaxial cell. We have a pulse transmission setup, some rock physics related instruments including microscopy and imaging. This is a porositymeter, and then we have also an absorption-desorption apparatus as well. But the two of the major instruments that I'm building, and they are almost done, one is a very high pressure temperature deformation apparatus that goes up to 500 megapascal pressure and 1200 degrees centigrade. This is called a kind of a Patterson type of apparatus, which is funded by IIT Kanpur Special Grant and Swarnajayanti Fellowship. And another is a triaxial deformation apparatus, mostly for rock physics and hydrofracking. The instrument has arrived in the campus, but yet to be installed and unpacked. So this instrument is also from IIT Kanpur Special Grant and Pan IIT ONGC research programs. In the next two slides, I would like to give you some views of these instruments, the way they are building, and you are for the first time seeing this instrument. This is a Patterson apparatus. I'll talk about it throughout the lecture later. So this is being built in India, and what you see here, this is the pressure vessel and different controllers here, and some electronic circuits. The other instrument is this one. This is also a multi-component instrument. These are the photographs when I inspected this instrument this winter in Germany. So you have the sample here. This is a sandstone sample, and this is how the sample stays here. These are some different sensors and pore fluid connections, and etc., etc. I hope I can get a chance later, maybe next year, to talk about more about these instruments and their results. So the way I decided to present this lecture is more or less outlined here. So at the very beginning, I'll talk about some sort of backgrounds and motivations, and with some deviations, I'll go a little bit in a teaching mode, particularly for the young students. And then I'll talk about strength rheology and flow laws of solid fluid mixtures. I'll explain what these are. And then, of course, a present-day understanding on the partial melting and crystallization. I'll talk elaborately on this. And then I directly jump into the experimental processes, the way we perform the experiments. Then I'll come to the results. And finally, I'll make some concluding remarks on the results of these experiments. So the first question, because I'm a structural geologist, a student of structural geology, the first question one should ask that how does a rock deform? And there are two different categories we can explain the rock deformation. One in terms of the types of the deformation, and another the rheology of the deformation. So in the types, we generally have two end members, brittle and ductile, and in between we have brittle ductile. And the rheological point of view, we have three end members of the rheology: elastic, viscous, and plastic. You already know this, or you'll be knowing this in the course of time. Now, these brittle ductile and brittle ductile, with the rheological terminologies, they are somehow different in terms of the way we look at it, but however you can combine them. You can say that all brittle deformations are somehow plastic, where you can consider the ductile deformation that includes everything which are not elastic and also not brittle, because ductile is some sort of a continuous deformation without losing the cohesion. We can also talk about the time-dependent features of this deformation, or rather strain rate-dependent features. So viscous is something which is time-dependent but neither elastic and nor plastic. And these three can be combined in many different ways. So we'll try, in this lecture, we'll try to see both in their respective ways through the experiments. But to start with, they are generally considered or conceived through the very basic diagram of stress versus strain. So here on the side, this 1, 2, 3, 4, 5 are some very classic experiments performed by Marvin Patterson. And this is the initial sample without any deformation, and then he increased the confining pressure in different samples, and then these should be the ideal stress strain curves. So the first one, it mostly produces tensile fractures or single or a few shear fractures, and then it fell immediately at its yield point. The third one is, as you can see, it did some barreling, so it underwent some sort of ductile deformation after the yield, and that's why we have this segment from this black to red here, and then finally it failed and it produced a numerous shear fractures. Number fourth is this one, where it significantly deformed plastically after the yield, and it has many numerous shear fractures, as you can see, one in this set and one in this set. We call them conjugate shear fractures. And the final one that was deformed at the highest confining pressure, that had almost, in the sample scale, you don't see any shear fractures, so it continues deforming in a steady state manner. So these are examples of brittle and brittle ductile domain. But in the ductile domain, when you deform the rocks in the high pressure and temperature, they don't produce fracture, but they deform through the mechanism of dynamic recrystallization. So this is an example of Carrara marble being deformed. So this is the initial sample, and this is how we deformed continuously. So this is the second one, this is the third one. This is shear strain about 2, this is shear strain about 11, and this is shear strain about 50. So you can see that how the grains are being rearranged through time. And again, you can explain this in terms of stress strain curves. So if I try to show you that in the vertical axis you have strain, in the horizontal axis you have strain, vertical axis stress and horizontal axis strain. You see that the crystals, they rearrange themselves by the movement of the dislocations, and a series of processes do happen through the processes of bulging, subgrain rotation, and grain boundary migration, and these are all processes of dynamic recrystallization, and eventually you reduce the grain size through this kind of deformation. Now these are some very simple experiments performed in the laboratory, but if we'd like to fit these in the bigger picture, like in the crust of the earth, or the lithosphere of the earth, to be very specific, see some kind of feature like this, what we call rheological strength profile. So in this side, so you see kind of a triangle here. So this side, the rocks behave in a different way than this side. So this side rocks are stable, and this side the rocks are not stable. So of course the crustal region, or the top part of the earth, is brittle. So it follows a rule called Moore-Coulomb failure criteria, and then in the deeper part it becomes ductile. Then the deformation feature behaves in a nonlinear manner. We can explain it with this equation. I can come back to this later. But interesting part is, in the brittle field, Byerly very well explains that it is not really a composition dependent feature. So here are different rocks that he deformed. Here you can see the list, and at confining pressure lower than 200 megapascal, he proposed that the rocks hardly have any cohesion, and the coefficient of friction is close to 0.85, but at higher confining pressure, that is higher than 200 megapascals, it has a cohesion of 0.5 megapascal, and this coefficient of friction should be 0.6. This is not 0.8, so this is a typo. But interestingly, you see that all the rocks here, they are in a very, they are following a trend. So composition really doesn't affect the, in general, brittle behavior of the rocks. The situation, however, changes when we go to the plastic domain. So these are again experimentally determined curves to figure out, and you can see that different minerals, different individual minerals, they show completely different curves. Their strength, their behavior, their curvatures are very much different. So to understand the ductile part of this deformation is extremely difficult, because in single crystal they vary a lot. Now you imagine that you have polycrystals, that you have multiple minerals in a rock, which is actually very common, and then this region, this plastic flow region, becomes extremely difficult, and this is where we need to perform more and more deformation experiments with sophisticated instruments. So here I'd like to deviate a little bit, and we talk about a little bit of the tools and challenges of experimental rock deformation. So tools that essentially you need some deformation apparatus, rock deformation apparatus with very precise measurements at different pressures, temperatures, and strain rates to snap the overall from the surface to the depth of the earth as deep as you can go. I'll show you what are the different instruments, but most of them are compromised. And if you talk about the challenges, there are many challenges. If I have to talk about the challenges, I'd take probably 2 more hours to speak on that, so I'm not going into that part. But one of the most important challenges that we face in the laboratory while we deform the rock is essentially the strain rate. We know that most of the geological materials are in natural way. The strain rate is extremely slow. So it goes in the order of 10 to the power minus 12 to 10 to the power minus 14, except some events like impact craters or earthquakes. Now, if we have to achieve the strain rate that happens in nature in the laboratory, you can figure out that this is 10 to the power minus 9 per second strain rate, which is still a few orders magnitude lower than the natural strain rate. So to achieve 10% deformation, you need 3.2 years, 20% 6.4 years, and 30% almost 10 years. So this is virtually impossible for a researcher because no one would give you the fund to run a 30% deformation experiment, a single experiment for 10 years. You won't get any students because they won't come to do work for 10 years with you. But most importantly, apart from this, some practical issues, there is also not any instrument where you can use this kind of strain rate. So we have to compromise in many ways while we perform the rock deformation experiments. So this is one of the problems that I stated, but there are many others. So from now on, I'll show you some of the basic instruments that we use. So for essentially brittle deformation, we use uniaxial compression apparatus. This instrument is pretty simple. So sample stays in the middle. We have load cell to measure the load, which you later convert to stress, and then some displacement sensor through which you later convert to strain. And then you have some hydraulic control or servo control power pack, some controlling units, and data acquisition. So this is a very simple instrument that you can see. So here is a sample in the middle. This is the load cell and something like that. You can deform rocks here either by compression or tension. Tension is a little difficult, but you have to grip the sample, and that is most of the time doesn't work, but the sample is soft, then you can perform the tensile experiments. The next instrument you can think of is the triaxial deformation apparatus, a very basic triaxial cell you can consider, where you keep the sample inside a confinement pressure vessel where you can have water or oil that comes through this hole and then pressurize the chamber. So sample stays under some sort of a confinement simulating the overburden load or lithostatic pressure. You can add furnace inside or outside. Here, for example, in this image, you see the furnace is staying outside. So it heats the oil or the water and provides the sample some sort of heat. And you have some temperature measurement units like a thermocouple. You need also pressure measurement units inside, together with our two known friends, load cell and displacement sensors. So things become a little difficult when you'd like to go to even higher pressure and temperature conditions. So there we have some very classical instruments. These are not available commercially, but one of them is Patterson apparatus that has a range of this is red. Then comes the Griggs apparatus, then D-dia, multi-anvil, and diamond anvil. And this 410 and 670, you know that these are the two transition zones in the mantle. So given this overview, we would like to now see that what are the different instruments and their ranges. But before that, let's have a look what could be the different deformation geometries that we can achieve. Theoretically, we have two end members of deformation, pure shear and simple shear. So in the experiments, we try to manipulate our designs to achieve either of these two. So one is the compression, another is kind of a shear cut, which is this one, and then you can have torsion, which I'll talk about most of the time of this lecture, and also the tension. Now, the problem of all these kind of experiments, or you can think of another challenge, is that I just tell you one, that for example, for these compression experiments, you see that the sample has bulged here. Now, this is an issue if you'd like to extract the mechanical data precisely, because we know that stress is force that you are applying divided by the surface area. Now you can see clearly that in this sample the surface area is not constant throughout. So your data that you will be measuring through the load cell is erroneous. So these is also for this tension experiment. You can see that here it has reduced the diameter. So it is, we call it inverse bulging. But we compromise with this. We go ahead and figure out what is the best solution to achieve an experimental problem. So here is a list of some of the instruments I said more or less. So these are ambient basic uniaxial apparatus. You can have some ambient pressure or low pressure to very high temperature apparatus, and these are used mostly for magma rheology, or people also work for diffusion experiments, and then slowly moderate to very highest, so where you have diamond anvil where you can achieve 370 gigapascal and temperature goes up to 2200 degrees centigrade. Now all these, this triaxial apparatus, these are mostly oil and water medium. This is a gas medium apparatus, and rest are mostly solid medium apparatus. We will not talk about this, but we will go only with this moderate pressure and high temperature apparatus, that gas rig Patterson apparatus in the following slides. So let's go back to our question, that melting in the deep earth, and to talk about this, because again I'm a student of structural geology, so I'd like to ask the question where we have most of the deformation or high strength zones in the earth. And if we plot them on a surface of the earth, we see that these are mostly concentrated along the plate boundaries. So these are characterized by mountain chains, mountain belts. These are earthquake zones. You have the explosive volcanisms, and these areas are also the most dynamic areas of this earth. And therefore, studying them, it's very, very important that what is happening there. And of course, there are many ways you can study them in different scales. Joao spoke yesterday in a very different angle. He spoke excellently. I'll take it to different directions. So among these, you know that there are some convergent plate boundaries, divergent plate boundaries, and shearing plate boundaries. And I'll focus mostly on the convergent plate boundaries, and you can think of specifically the subduction zones. So if we think of a subduction zone, this is a cartoon diagram. So this is the oceanic crust which is being subducted over an continental crust, which is this one. So at the very beginning, shallow depth, we know that we have earthquakes here. These are, we call Benioff zones, where it is locked. But when this slab goes further down, then it experiences much higher temperature and pressure, so it undergoes some sort of dehydration melting, and it melts the rock partially. Now these melts, they originate at the grain boundaries. Then there are some sort of pressure differences, and because of the pressure differences, the melts to migrate like this, because they are buoyant, so they flow upward, they stay in a kind of magma chamber, and finally they erupt through volcanism. So that's a very, very common general situation that we learned in our classes. And if we take this particular region where the partial melting is happening, or dehydration melting is happening, we can see that we have a series of features that you can think of. So on the top you have some fractured zones, then aligned silosilicates, or even crystallographic preferred orientation of some deforming minerals. Then you have melt-rich shear bands, and then at the end you have tectonic elements. So if you have any earthquake or something like that, the seismic waves, they have to pass through all these. And all these features, they oriented differently and they continuously undergo reactions. So the seismic signatures also do alter. So in this presentation, we would like to ask the questions, the general question, that what is the fate? So here you have some sediments which are being deposited on this subducting channel here, and these sediments are being dragged through this. So when they arrive here, what is the fate of this sediment? And this is exactly what we are going to look at in this presentation through some novel rock deformation experiments. So before that, let's have a look of what people have done so far in this. This is not a very new question that we are going to ask. So we know that subduction, that solid rocks undergo partial melting, and then in abduction they again become solid. So you can think that this is a cycle. So from here to here, these people, Vinerese, Tikoff, and Gould, they proposed some sort of percolation thresholds based on the crystal melt ratio in the system. So they have proposed LPT, MET, RPT, and PLT. I'm not going into the details, but there is something that one guy in 71, RZ, he proposed, that rheologically critical melt percentage. Why this diagram is important? Because it gives you it determines the strength of the lithosphere or the particular rock that you are concerned. So if it is rock is a solid, it has a different strength. If a rock is molten, fully molten, it has a different strength. And then you have an n number of possibilities between the solid and liquid. And depending on that, the rock can lose their strength at a particular time or a particular melt concentration. And this is called rheologically critical melt percentage. We don't have a very significant theory for that, but generally people approach a theory that is Einstein-Roscoe equation. We'll come back to this, but if we have to look at the deformation of solid and liquid together, then it gives you a wide range of ideas or a wide range of solutions for different features that we see in the earth. So it could be the partial melting in the subduction zone that we will be talking about, then mild migration through porous media, the viscosity and rheology of the melt as well, then dike and batholithic intrusions in the continental crust, the dynamics of the magma chamber, and overall the volcanism and magma flow. So this research has a series of implications. But when we talk about the solid and liquid melt and how do the strength of this rock change, we have some classic equations. There are some complex equations, but I'm not going into that part. But the fundamental equation comes from Einstein in 1906 and 1911, where he considered some rigid particles. They are spherical in shape and equal size. And if their concentration is C and the fluid or the melt you can consider the viscosity is eta 0, then the effective viscosity of the aggregate is given with this linear equation. And people showed experimentally that this holds good when concentration of rigid particles is less than 50%. But later Roscoe modified this equation and he came up with a nonlinear equation where it holds for all values of C. So if we try to plot this Roscoe equation, then it gives a slope, a curve like this. Now you can ask this question very beginning that this equation is mostly for suspension. So whether can you consider a partial molten rock as a suspension? The answer typically is no. But when people run experiments with different concentration of melt in the system, they found that at least 40% melt fraction, it generally follows the Einstein-Roscoe equation. But apart from the rheological part, it has also a very important implication in localization of the deformation, which I try to explain in this cartoon diagram. So if we have two grains touching each other and you are applying a force in this grain, then this grain will transfer the stress to the next grain easily because they are in a solid contact. But if you have some melt in between, then the stress you are applying to this grain, it cannot transfer directly to this grain because you have a melt, so the melt actually takes the entire strength. And this is how you partition the strength. The strain is not homogeneous in the system, and therefore you induce localization. So, and this is a very basic concept of deformation, that weakest phase actually governs the rheological behavior and strain localization of multi-phase systems. And this is the reason you cannot transfer the stress from one grain to another grain to achieve a homogeneous deformation. So given this context, if we see that what is the manifestation of this strength transfer, or what is the manifestation of the deformation of the rocks, then we have one very key important terminology that we use in the rock deformation is this term N. So let me explain this equation first. So this is strain rate, which equals to a material parameter A. This is the stress. This is the stress component. This is minus Q, which is activation enthalpy. R is Boltzmann constant, and T is temperature in Kelvin. So as you can see, this is a nonlinear equation. The challenge of the researcher is to figure out this N value. The importance of N is that if N is 1, then you can see that this is a linear equation, and if N is not 1 or greater than 1, then it is a nonlinear equation and the flow is non-Newtonian. If it is 1, then the flow is Newtonian. So experimentalists determine this N value by running some experiments, because if you transfer this equation in logarithmic form, then N becomes log of strain rate divided by log of stress. And this is what people tried in different ways. And you can see that the stress exponent, which typically stays for non-Newtonian rocks from 2 to 5 or sometimes to 7. But here you see from a single experiment, this N was Newtonian, then it becomes non-Newtonian, and so on. So you see a transient rheology is happening. The N value is not remaining constant, and this has also been observed to other experiments. So with this background, we can ask these questions that partial melting in a solid polycrystalline rock significantly lowered the strength, that we have seen that if you introduce fluid in the system, you can think of a solid compacted sand or sand with water. So sand with water is certainly have much lower strength than a compacted sand body. So that is very well known. But what happens if you slowly try to take out the water, or if you try to reduce the concentration of the partial melt, and then these rocks start crystallization? So we would like to see the entire picture, that you have a solid rock, then you produce melt, and then again out of the melt you are producing new crystals, and the rock again becoming a solid. So what is this entire behavior of this rock? If you'd like to see, can we track this? And what is the overall dynamic environment, that how much finite strain and how much finite strain you need to effect of the partial melting and crystallization? And here you can also ask the question that whether deformation is playing any role in producing the partial melt or not. And of course, finally, you can check this, whether the bulk rheology of such systems have any implications with the microstructures, the deformation, and in general the large deformation. So these are the questions we are going to ask in this presentation, and we'll see how we can interpret this one after another. But again, I repeat, this is not the question that we are asking for the first time. So people have performed analog experiments. So for example, this one is done by Rosenberg and Handy. So these are NOR-camphor, which is solid, and benzamide. He thought this is a kind of melt, and he figured out that a low angle shear bands, or in brittle deformation term we can call it riddle shear fractures, the benzamides are concentrating here. In a very similar way, Chatterjee proposed a numerical model where he also showed that along these low angles the melt get channelized and then they percolate to the magma chamber. But these two experiments, or numerical or analog experiments, you see that they had melt from the beginning in the system. So the melts, they just organized themselves and found their ways, or in the numerical model, it is some kind of a porosity waves and so on. But experimentally, it has not been demonstrated that you are producing melt and you are also producing new crystals out of this melt, and then you try to track the entire picture in terms of mechanical data and microstructures. And this is what we are going to do now. So to do that, you have to make a very good strategy, and the strategy is, of course, a large strain rock deformation experiment. As we have seen that with the compression or tension experiments, you cannot achieve really large strain because you have to go to see the entire picture, a very large strain, and then torsion experiment is only way to do that. I'll explain you why and how the torsion experiments do work in some later slides. But we selected some materials, quartz and muscovite, as the very common composition of the Earth's crust that can undergo subduction. We had to fabricate the samples, we had to characterize the initial sample, and then we selected some classic samples. The quartz we used is simple quartz with a very smaller grain size, and similar with the muscovite. It had a little bit of iron, which had some implications. I'll talk about it later. But again, it has very small grain size. We selected smaller grain sizes simply because at high pressure temperature, we want them to react. So smaller grain size would react fast. The pressure we used 300 megapascals, that's the confining pressure, or you can think of the lithostatic pressure or overburden pressure. Temperature we used 750 degrees centigrade. I'll explain you why. The strain rate we selected in this manner. So 1 to 3 into 10 to the power minus 4 per second, but I'll only show you this. And this is a very easy strain rate in the sense that if you apply this strain rate, then one magnitude of shear strain or one gamma requires about 1 hour. And we could go up to shear strain 15, so we could run an experiment for 15 hours. And after we have seen these experiments, we performed these experiments, we post-processed the data. So we worked on the mechanical data, we checked on the microstructure, we did some chemical analysis, and we also performed some thermodynamics. I did not do that, but some of my collaborators did this. And I'll explain you one after another how all these things work. So we performed several experiments, but here I'll only show 70% to 30% to 70% experiment. That means 30% quartz and 70% muscovite. So this is how we have prepared the sample, and before that, because we prepared a synthetic sample and we used high pressure temperature deformation apparatus to synthesize the sample. Some noises are coming here, it's got. So this is the reaction curve of muscovite quartz, and we kept the synthesis pressure and temperature just above this so that it doesn't react and produce any of this. So we first do some uniaxial compression, then here we hot press the sample at 180 megapascal and 590 degrees centigrade for about 30 hours, and then you get the solid sample out of these powders. Now these synthetic samples are very important because, I mean, of course you can work samples from the field, but you need multiple samples, and if you work samples from the field, these samples could be heterogeneous. One sample to other sample could be different in terms of their physical properties, grain size, and so on. But here in this canister, I know all these samples I code, they are very similar. So the initial microstructure, the initial physical properties in all samples, they would remain same. So I'm safe if I have to run multiple experiments with this synthetic sample. So this is the initial microstructure. You can see here observed under scanning electron microscopes in BSc mode. So these are the thin layers you see. These are muscovites, and these blocks are quartz. These are some zoomed view. The XRD analysis of these initial samples showed that it has only quartz and muscovite, and then we did some TG experiment, thermogravimetry experiments. What it does that you heat the sample slowly and see the weight loss. So muscovites, they do dehydrate, and then because of the dehydration you see the weight loss, and this is what we have performed. So here we lost about 1% of water, and we assume that this is the water or moisture or grain boundary waters, but this is actually because of the dehydration of the muscovite, and it happens mostly between 600 to 800 degrees centigrade. So 750 degrees centigrade, therefore, is a suitable and switch temperature where you expect that the dehydration melting would occur during the deformation. So that justifies why we have selected the 750 degrees centigrade. So this is the instrument, a very similar instrument will be arriving in IIT Kanpur soon. And here you see three Pattersons, Marvin Patterson himself and two of his instruments. This is the pressure vessel and this is the torsion motor. I'll explain how does it work in the next image. And yeah, this is how it works. So it has several components. So this is again the pressure vessel. And you have axial actuators, so you can compress the sample, but this is not what we have used. And this is more or less the cross section. So this is the sample here again. Then you have series of pistons, we'll see in the next slide. Then you have furnace to heat the sample. And you have an internal load cell to avoid any friction, so it directly touches the load cell and measures the load. So this is the specimen assembly. You can see this is the exact quad muscovite sample. These are the pistons or anvils that you can think of, and they get attached to the torsion motor here. So this tip is this one, and then this one is attached frictionally with this. This is the motor, and here you have a series of gearbox. So you apply the deformation from here, and then it rotates, reduces the gear, and then it drives this, and apparently it deforms the sample only. Now here is a very basic question that you may ask, that what is gripping the sample, because all these are loose as you can see. So if you twist it, then you may have slips from here. Now yes, your question is right. So only one condition, that the friction between these surfaces has to be higher than the strength of the sample. The frictional strength here has to be higher than the strength of the sample, then only you can deform the sample. And the frictional strength between this is being increased by adding the confining pressure to the sample. You can imagine very simply that we can twist our towel. After bath, when we twist our towel, then we can twist it because we have a grip from our palm to the towel which has much stronger grip, that means much higher friction, and the strength of the towel is much less. So you can twist it. But you cannot do the same with an iron bar of similar diameter, because the strength of the iron bar is much higher than the friction between our palm and the iron bar. And this is exactly the principle we use here. This is the deformation geometry, some sort of ideas that how do we work with the torsion sample. So clearly this is rectangular, cylindrical geometry. You need to consider this is the rotational movement, and at the center the deformation is 0. More you come towards the periphery of the cylinder, you achieve higher stress and also higher displacement, and therefore higher strain, shear strain. So this is calculated by this equation, d alpha by dl. The gamma or shear strain maximum is here, which you calculate with this equation, and the shear stress is calculated by this equation. So you have to know the stress exponent, and this is how you calculate. Here T is the torque that you are measuring, R is the radius, and this is how it works. And once you deform the sample, then you can look at many different surfaces, but we'll see only two surfaces. One, we call it longitudinal tangential section. So as you can see that this is where the strain is maximum. So if you cut this section and if you observe it here, you actually see a plane that underwent a significant simple shear. You can cut it also from the middle of the sample, and it gives you an excellent transect of shear. So here you have shear strain 0, and more you come to this side, you can actually see that how the overall strain has increased. However, this is not a classical XZ section that we generally look for shear zones, but this is essentially an XZ section. You can equate it with the XZ section. So this is more reliable to understand the shear kinematics and other things, and this is more reliable to understand few other features, so we'll talk about it later. So once you deform the samples, they look like this. On the outside you have this iron jacket that you can see here. So if you have a homogeneous composition like calcite inside, so you see these were some straight lines and now they have rotated and they make this wheels like things. But if you have some shear localization, then the print of the shear localization also comes on these jackets, and you can see these low angle shear bands have arrived here, and these, if you see this in the field, this kind of features, you say, oh, this is extensional granulation cleavage, or you say that, oh, this is C prime features, and exactly this is the same that we produce in the experiments. But if you have shear localization, then because these are metals, so they get hardened more, and you can produce some holes in the jacket, and if that produces, then you're gone. You have to stop the experiment because you lose the pressure very quickly. Luckily, we didn't have that in our experiments, so we could happily go to 15 shear strength. So now I'll show you the experimental microstructures, and the way you will understand, I will have a series of slides. So this is the initial microstructure. You can see this muscovite and quartz here. The samples were like this, twisted. We observed on the surface, on the XZ section, and this would be the deformed microstructure. So in this case, this is shear strength 1. We more or less see the same scale of these two, so initial microstructure and deformed microstructure, so that you can compare how it is deviating from the initial to the stage we will be looking at. These two little white, black and red lines would indicate the magnitude of strain. So this is the vertical, and this would go, so this is now 45 degrees, defining that it is shear strength 1. And with more shear strengths, we will see that these red lines would try to slip more. And how does it work? And in all experiments, the sense of shear is top to the right. So let's start with this. I repeat again, all these experiments were performed at 300 megapascals and 750 degrees centigrade with a strain rate of 3 into 10 to the power minus 4 per second. So you see here the initial microstructure, it was pretty much horizontal, the muscovite layers, but here they already started rotating in response of the shear at shear strength 1. We also see that the porosities we have in between the muscovite and so on, these are much more compacted, at least where we have muscovite and quartz, but within the quartz grains, because of the strong network of the quartz, the porosities are still open. Let's move to the next one. This is shear strength 3, and this is what you see from this red line. We see that some little white dots here, so now some new guests in the microstructure. We'll see later what these are. But again, we see that muscovites are getting broken here and there. But if we go to the next increment, this is shear strength 5, we see that from the initial microstructure to here, we have a significant change. Shear strength 5, that means it has been deformed for 5 hours. And through some analytical techniques, we figured out that these whitish, the brightest phases that you see here, these are some spinels or biotite. They are really submicrons. We really could not understand exactly their chemistry. You see some euhedral crystals here and there. These are potash feldspars. And then we have some pockets here and there. These ones, and these are melt pockets. So we have produced melts. And we also see some tiny fibers, and these are siluminites. And we'll see whether this is thermodynamically viable or not. To move on with more deformation, to shear strength 7, we see that we produce some sort of shear zone microstructures where you have these are low angle shear bands or C prime, and then you have also the S kind of fabrics. What is interesting here, you see that all muscovites are almost gone. You have remnant of quartz grains. The grains are a little rounded because they took part in the melting reactions. There is feldspar crystals are really high in the system, and you also have melt pockets here and there. And you can see the magnitude of strain with this red line. This is shear strain 10, and you see the microstructure is completely different. You also see some shear zone induced microstructures by these sigmoidal features and so on. Quartz grains are very much reduced in their size. Feldspar are very much dominating, also the sillimanites and so on. And this is shear strain 15. We don't have any melt here. We have quartz, remnant relict quartz grains, we have feldspar, and we have biotite and other spinel minerals. And we form this kind of fractures. So this was, we can consider this was a tensile fracture or maybe rotated high angle riddle shear fracture and some low angle riddle shear fractures. And I remind you, everyone, that this happened again at 750 degrees centigrade. So at such a high temperature, you can produce fracture if the melts are gone from the system. Well, I did not drain them, but they got crystallized to produce some new crystals. So it became again dry. It doesn't have any melt, and it produced fracture at 750 degrees centigrade. So to summarize this, if we try to look at, so these are the macro features, the way you twist the samples, and these scale of this upper row images were about, say, 250 microns, and the bottom is about 10 microns. So you see that you produce here this melt channels, right? So this, the orientation is very, very similar to the C prime orientation, and here these are full of melts, and these are exactly similar to what has been produced by analog experiments and numerical model by Rosenberg and Sarge. So if we look at the reactions, so we have seen that it has produced some new minerals. We did XRD, and we figured out that we had quartz, orthoclase, ilmenite, biotite, and spinel. So initially we had quartz and muscovite, and this is the reaction. We did some analysis, thermodynamic analysis with James Connolly using his Populax, and the composition we gave him, and he figured out that this is exactly where it should be at this pressure and temperature we used, and this is the composition we should have theoretically, and this is what we got. So this is a very nice match from theory and experiment. We also tried to figure out that which phase is contributing how much and which phase is showing out or popping up how much with this, so contribution of the phases, and there we have performed some experiments without deformation. So that means there is no deformation, only pressure and temperature, same pressure and temperature for the similar time. What is interesting is the red curve is the melt. You see that in deformation experiments, these melts, they reach up to 20%, and then they lower significantly because of the crystallization. But when you don't have deformation, the melts continue staying, so then they don't drive crystallization of the rock, recrystallization of the rock in a different way. You also see that new crystals, so these are mostly feldspars, in deformation experiments they are much more higher compared to the static experiments, and this is quite understandable because these are being produced through the at the expense of the melt, but here not. So if you have melt here, you cannot produce much feldspar. Now muscovites is very interesting. The dehydration happened very fast. So about, we have seen that around shear strength 7 to 10, all muscovites were consumed. But here, at least to shear strength 14, we could see the muscovites and other phyllosilicates. So this slide clearly states that there is a significant difference of reactions if we have deformation present in the system and if we don't have deformation present in the system, and we'll talk about this later more. So let's look at the mechanical data of the system. So this is the entire span and all these experiments. So yield was somewhere here, and then it deformed plastically. the peak strength we achieved about in terms of torque, somewhere about 35 to 30 Newton meter. And we remembered, we'll see this, that the strength significantly reduced, almost 60% strength reduced at this stage, say for example shear strength 1 to shear strength 3. Then it more or less flowed in a steady state manner. We have seen a little increase of strength here, and then finally at shear strength 15 it produced a fracture, and that's why the strength significantly reduced. So it actually mimicked what we have seen or what we could expect from the microstructures. Now, if we try to divide it in different ways, different segments, and try to figure out what would be the N values or values of the stress exponent, then we clearly see that at this stage where we started generating the partial melt, the stress exponent is 5 or 3.78 even here. Now, this is very important because at this time, this is still flowing, this is still ductile, and this is more or less behaving in non-Newtonian manner. But when you go to the higher stage, so these things, the stress exponent is extremely higher and it becomes plastic. So it goes up to 43 stress exponent. And no surprise, it produced a fracture at shear strength 15. We can see this in a different way, or classify it in a different way. So at the very beginning, up to shear strength, say 0.7 or something like that, we have solid state deformation. Then we have partial melting dominating time here, say shear strength 0.7 to almost 3. Then this is the most important domain where we had both partial melting and crystallization went on together. And finally, after shear strength almost 9, we had mostly crystallization from the melt went on. So we see that transition, there is certainly a transition from rheology, which you have seen from the previous slide, that the N values changed from almost 3 to 50. We saw the microstructures, we saw the reactions. So all these can be clubbed together, and the transition of rheology can be explained through the chemical reactions. And all these things can be put in a picture, in a single picture like this. I'm not sure if you can see this. So here I have plotted or brought this phase features. So this is how different area percentage with the magnitude of strain. This is the stress strain curve. And this is where I have divided them in different domains. So muscovite stays till this. From here to here you have melt, then crystallization occurs here, and then a continuous change of rheology from N4 to N40 in response to the different features. And also in terms of microstructures, you can see that original layers initially got distracted, then you have isotropic microstructure, then you form C prime fabric, then C prime S fabric, then S fabric, and finally it produces brittle microstructure. So we see a range of features that you can produce through an experiment and see what we mostly see in the field. And these are also the summary diagrams that you can figure out from this. We also tested, as I said, that we have many features in this top part of this subducting oceanic crust. So we tried to see the ultrasonic velocity, that how does it change when you have partial melting and crystallization. So it's in a similar apparatus. Instead of deformation, we added some transducers which can resist some high temperature. The sample stayed here, and we calculated, or we calculated the longitudinal velocity out of the ultrasonic velocities, and we see that at the beginning, the 3 different samples, when I oriented them differently, their foliations, they behave, their velocities are different. So the red ones are when the planar fabric is oriented 0 degree, and this is 90 degree, and the green ones are 45 degrees. So you see with time, when you come here, that they actually approach isotropy, and this is essentially because the muscovites, which are the most anisotropic minerals in the system, they actually produce melt. So they are becoming less in volume in the system, and therefore the anisotropy of the system is reducing and the entire system is approaching anisotropy. So this is a very simple word, but it has an implication. I'm almost at the end of my lecture, so I'd like to give some concluding points on this. So first of all, which is not written here, experimental rock deformation is very, very important to understand directly some features that we don't see happening in the art, but it can give us a first-hand idea and also sometimes a very crucial and important features or important ideas that can be fed later in numerical modelings or in theoretical modelings for better understanding the behavior of the deformation of the art and so on. So particularly for this study, yes, we have demonstrated that there is a transient rheology in action, and the rheological transition of the bulk system do happen due to a partial melting and crystallization from the melt, so at different stages. The new minerals, they greatly, their formation greatly depend on both finite strain and strain rate, which I did not show here. But yes, finite strain, we have seen that there is significant difference between when you deform the rock and when you don't deform the rock. And we, in the last slide, we have seen that the system is less seismically anisotropic after the dehydration, and velocity and anisotropy reduced due to a breakdown of the muscovite melt production and circulation. So with this, I conclude this lecture, and this study has produced a few number of papers. So if you are more interested to look at all the different directions of this work, so here are the publications, you can have a look. And I acknowledge my advisors, starting from my students' life, Professor Ghosh, Professor Sengupta, Sutta Sengupta, Professor Mandal, and my advisors and colleagues in IIT Zurich, John Pierre, Luigi, David Price, and of course Martin Patterson. My postdocs, PhD students and master students, lab technicians, the reviewers who contributed significantly in this work, and certainly the funding agencies. So thank you very much everyone for listening this talk, and I'm done.
I would like to thank Dr. Misra for such an enriching and interesting lecture. We will surely return this day more knowledgeable than we got up. So let us take a 5 minutes break while we compile the questions that we have received from the participants, and Dr. Misra would surely love to answer them. On a different note, I would like to remind everybody that next week on 29th August, we shall be having with us Dr. Swarnajayanti Ghosh, Assistant Professor of IIT Kharagpur, and he will be speaking on applications of high pressure research in earth sciences. And on 30th August, we are going to have with us Dr. Masako Yoshikawa, researcher of Hiroshima University, Japan, and she will be delivering a lecture on deciphering petrological processes using geochemistry of peridotites, a case study of the woman of rheolites. We are really very thankful to all the participants for such a wonderful response to our initiative. Okay, now that we have received the questions, we are going to start the question and answer session. Owing to the vast multitude of questions we have received, we won't be able to accommodate all. For that, we are very sorry. However, we shall try to take as many possible to the speaker within the stipulated time. So we are now ready to discuss few of the queries that we have received. For the first question, I would like to call Dr. Misra's attention. We have Mr. Rishu Pandey, UG student from Mahatma Gandhi Chitrakoot Gramodaya Vishwavidyalaya, India. His question is, for melt flow index test, which are the drying temperatures and time to choose for hygroscopic ABS and PA polymers prior to the measurement? What techniques are used to increase the Torsion ratio of polymer melts?
Would you please repeat the question again? I could not hear it properly. So.
Yes, sir. Yes, sir. For melt flow index test, which are the drying temperatures and time to choose for hygroscopic ABS and PA polymers prior to the measurement? What techniques are used to increase the Torsion ratio of polymer melts?
Okay, hello, thank you for this question. But polymers, they do behave absolutely differently than rocks, the melt of the polymers. First of all, polymers melting temperature is extremely low. I think 120, 130 degrees centigrade melts. I really am not an expert of this topic. You may contact me later. We can discuss directly because I also didn't understand the question properly. But yes, there are many deformation experiments. You can think of rheometer, which has a temperature added to this and a little bit of pressure. Nowadays, it's available. There are many companies who produce this. So in rheometer, you can actually get a lot of rheological parameters, and it goes up to 200 to 250 degrees centigrade, so should be absolutely fine with polymers. I think people do work on that, but please come back to me later. I'll try to answer this question in more detail.
Okay, thank you, sir. For the next question, we have Shorbhanu De, Presidency University. On what conditions ultrasonic velocity does depend, and what are the lithological conditions, and what should be the crystal melt ratio?
Well, ultrasonic velocity is some sort of very scaled, how should I say, scaled up or scaled down. Let's say scale down experiments in the laboratory. So these are not like, of course, these are kind of acoustic emissions. You can make an analogy with the seismic waves. So we use a very high frequency, few kilohertz to megahertz in the laboratory because we had to pass it to a smaller diameter sample, not the entire Earth. And your question is, it depends on many things. Of course, I mean, it follows the equation of P wave and S wave. So the denser rocks would have higher velocities and so on. So it's very standard and straightforward.
Thank you, sir. For the next question, we have Mr. Swarnendu Roy, PG student, University of Delhi. How does the polycrystallinity of a rock affect the deformational pattern?
So yes, I mean that's one of the very forefront research areas that if you see a few papers coming up in recent 5-6 years, that role of second phase. So yes, I mean they do deform because if you have 2 different minerals or 3 different minerals or 4 different minerals, then in an aggregate, individual minerals behave differently. And it has been established that the weakest among all these minerals would control the deformation because that would take the most strain of the system before it goes to the localization phase. So this is how it works. The weakest phase controls the entire rheology. So it has 3, I mean you can guess the 3 stages. So you start the experiment, then it goes to the yield, and then you assume that some sort of homogeneous deformation. Then the rock has to think that whether I should accommodate the strain I am receiving throughout my system, or I channelize through some particular zone or through some particular minerals. And this is the point of bifurcation. And if it deforms homogeneously, then you can consider the rock is mostly isotropic, or the composition is very much same. But if you have different minerals, then it has to localize the deformation because it cannot continue deforming each and every different mineral in a very similar way. So weakest minerals would deform faster, therefore it localizes the strain, and you have a heterogeneous deformation in the system, and eventually it would localize the deformation. So this is how a polycrystalline system would work. under deformation.
Thank you, sir. Next question we have Mr. Devjit Pathak, PG student, IIT Kharagpur, India. Can we use fractals to determine the complexity of the interaction between the phases and to understand their percolation?
Yes, you can. You can. You have to do a very detailed measurement and image analysis. A box count may not work unless you have really a very good images. But from this kind of experiments, yes, that's actually a good idea. I mean, let's talk more on this. I did not think of. So people do work on the dynamic crystallization, the grain boundary serrations and so on, and they did a lot of work on this, but not the aspect you told. So this is certainly a good idea. But yes, you require a very detailed and precise measurements of the features that you'd like to check with the fractals. Yes, it is possible.
Thank you, sir. Next question, we have Rohan Roy from Presidency University. What type of rock composition could you consider for those experiments? Pyrolite type or anything other?
I cannot answer this because I never worked in this direction, but generally say in general way that if you would like to, so we try to keep the compositions very simple. We don't want the system to be very dirty because we have so many parameters. We don't want composition to play some additional parameters. So for example, if you'd like to work with granite, then we simply take powders of quartz, muscovite, some feldspars and so on, a little bit of amphibole if you want, depending on your choice, and then you grind them and you cook them together. I really cannot answer what is required exactly for pyrolite, but it depends what you would like to see out of it.
Thank you, sir. For the next question, we have Mr. Manobendra Kuiri, PG student of IIT Bombay, India. His question is, what would happen if water is introduced after generation of melt and before the crystallization?
In experiments, it is very difficult. Actually, by introducing melt, you are introducing water. So, because it's a dehydration melting. So, muscovite has OH in its composition, and at that particular temperature it dehydrates. Of course, it doesn't stay like in water form, so it produces melt. But if you think of injecting water in the system, it's very difficult experimentally to do that. But if you can, hypothetically, then you actually increase the pore pressure of the system. So effective strength of the rock would be significantly lower, and most importantly, it would produce more melt. Because this is how it does. Of course, it has to have more other phases to contribute to this. The viscosity of the melt would reduce significantly. The melt percolation would be much easier because you are adding more water. But this is something we probably don't look at, and experimentally it is not, at least in my idea, it is not possible that giving you can extract the melt from the system by using some porous spacers that you have low pressure zones, so melt can get sucked, and Irata performed a series of experiments on that. But introducing melt or introducing water to the system, I'm not aware of, and I think this is very difficult to introduce at the time.
Thank you, sir. We have some more questions. We have Dr. Arindam Sarkar, postdoctoral fellow of IIT Kharagpur. His question is, for your high pressure experiment, you have shown a few photomicrographs at shear rate 5, 7, 12, etc. In this picture, you have shown different minerals like biotite, muscovite, etc. According to your photographic scale, the grains are lesser than 1 microns. How did you measure the exact composition of grains?
Well, I did not measure the exact composition of the grain. So I got it through XRD. And by their shape, by their it is actually not possible. In fact, few of the grains, now I'm doing EBSD of these grains. and we also had cordierite, which we could not figure out of this. So it's very nano scanning we can figure out. So microprobe, forget it, you cannot get it because the grains are sub-micron scale, and the diameter of microprobe is about 2 microns or so on. So these are not exact composition. I did not show the composition of the grains anywhere, but these are calculated thermodynamically, and also by XRD we could figure out that these are the possibilities. I think I showed the XRD now.
Thank you so much, sir. For the next question, we have Dr. Shubhadeep Bhadro, Faculty of Pondicherry University, India. Considering an open system, what will be the impact of partial melt loss on the rheology?
Hello, Shubhadeep, glad that you are hearing this. Yes, I mean, in an open system, the melt would escape, and eventually you'd end up with a kind of granulite. Right? The rheological consequences you can think of at the very stage. So, in experiments we produced fracture, and my idea is to that is probably because of the strain rate. But in nature, if it stays still at high temperature, I think it would continue producing the dynamic recrystallization, because if you see these in these experiments, as I said in the beginning, these are compromised in many ways. So the pressure was extremely low compared to the melting and other things. It is only 300 megapascals or 0.3 gigapascals. So I think with high pressure, it would deform or it would behave differently. But yes, I mean, if you extract the melt, it would solidify much faster. You don't have that much of feldspar and other minerals deposition, as long as it can do it in a solid state manner. Yeah, that's it. I mean, but to very specific, yes, you will produce granulite and some other minerals.
Thank you, sir. Can you please spare some more minutes in answering some few questions? We are getting a lot of questions. So we have Shubroto Ghosh, Associate Professor of Geology, Durgapur Government College. His question is, will there not be a gradient in strain in a longitudinal sense in the torqued specimen, in addition to that, from center outward in a cross section?
Theoretically, if you consider that this cylinder that we have deformed in torsion manner, if it is ideal, elastic, isotropic, and homogeneous in nature, the three terms we always say, and I did not say it, then yes, it has to be linear. But in our experiments, it is not. But we assume that it is linear. Otherwise, I mean, the non-linearity calculation, it is possible. I performed in one of the experiments. There should be a gradient, and this gradient would influence significantly the system. But the diameter of the sample, if you see, is very less. It's about 10 millimeters. So the radius is 5 millimeters. So in these 5 millimeter, we assume that it is extremely less. But I agree it is possible because the system is neither isotropic nor homogeneous and nor elastic.
Thank you, sir. Unfortunately, due to time constraint, we would have to wrap the session up now. So just a final question from me, that is, can we use statistical physics model percolation theory to model the fluid percolation in porous medium?
Yes, people do that. I mean, if you would like to do it in a statistical manner, you need a significant amount of data, which we don't have. But otherwise, the porous flow and other things, these are very well engaged in explaining this. So the work that I showed of Rick's cards is actually based on porous flow theory, and other work of James Connolly and others. They also work a lot on this melt percolation and other things. And this not only the melt percolation, but in general flow of fluid to porous media. It goes everywhere. Just you have to change the parameters and the models as well.
Thank you so much, sir, for sparing so much time in answering the questions. We now have almost come to the end of today's lecture of GEOCHRON 2020. We are really very grateful to Dr. Santanu Misra for taking out time from his busy schedule and sparing those patient minutes in listening and answering the questions. We hope to maintain this relationship of love amongst us. We would love to have you again with us in the future for any such lecture or workshop. Please visit the department and Presidency University if you happen to find yourself in Kolkata. Thank you so much, sir. Thank you so much.
Thank you very much. Thank you. I really enjoyed. Thank you very much. Thank you all faculty members and students of the department and also the viewers. It is overwhelming and such a large number of people have joined to this lecture. Thank you very, very much. Thank you.
We will just take a screenshot to preserve the memory. So,
Thank you, Shantanu. It was nice hearing you after a long time.
Thank you. Thank you.
It was a wonderful talk, Shantanu.
Thank you very much. Thank you.
Thank you, Shantanu. Thank you very much for the wonderful talk.
Thank you. Thank you. Thank you for inviting.
Yeah. I'm sure there will be a lot of questions from students to your mailbox. Because it is so much intriguing talk. There are a lot of questions must evolve, and I'm sure of that. You'll be receiving so much of mails.
Right. But I thank Shantanu to wrap it within 1 hour. So we had an half an hour session at least. So other questions she will obviously tackle from his mailbox. So there will be a lot of questions.
Or the students can compile these questions and send it to me. I'll try to answer them.
Yeah.
And then they can also forward it to the people who ask the questions. So that's also a possibility.
Yeah, that is a very good suggestion. Ankon and Ritanuka, you please take note of that. All the questions that you have already received, put it in one single document so that.
Sure, sir. Sure, sir.
How's Manav
doing?
Thank you
so much, sir.
In fact, there are many people watching in YouTube. It's very difficult for them also to really ask questions. I'm sure there are many there waiting with many queries, and they'll be really writing to Shantanu soon. I'm sure of that.
I'll do that. Nilanjana Manav is in Kolkata. So
Kolkata now.
He will be submitting his thesis soon. So it's done. Open seminar and other things are done.
Okay.
He is doing the best he does, eating and getting wet.
Okay, then, Shantanu, I think we have done.
You have something more to say, or we just have you taken the screenshots?
Yes, sir. Already taken. So stay safe, sir, and take care.
Thank you very much, and you also please do take care. Thank you very much. So shall I log off?
Yes, you can.
Thank you very much. Thank you.
Thanks a lot, sir, for taking out some time.
Yes, sir. Goodbye, sir. And have a safe and nice week.
Thank you.
Thank you.